I hope you can hear me. Yeah. Good evening, everyone. My name is Sandeep Yadav, and I am presenting my presentation titled as Techno Economic Assessment of Satellite LNG Regasification System, utilizing LNG cold energy for the cold warehouse facilities. This work is supervised by Professor S. Srinivas and Rangan Banerjee of IT Bombay. I thank all the organizers of MIT FSB to provide me the opportunity to present this work. The motivation for this work is when we that LNG is the most economical way possible for the overseas transportation of the natural gas. But what happens when we liquefy that natural gas? Lot of that energy that we supply is stored as a thermal form of energy, because LNG is liquefied at minus 162 degrees Celsius, and it is stored at the temperature and transported at the same temperature. When it is when it is utilized for the end consumer use, it is again needs to be regasified. When it is regasified, that amount of energy is that stored in the thermal form of energy, we call it as a cold energy. It's usually gets wasted. This is a typical LNG vaporizer, which uses seawater as a heating fluid for the regasification of the LNG, in which we can see all the thermal part of that LNG is getting wasted into that seawater that can be utilized for some potential cold energy applications. Now, in summarize, we can say that no, we can't utilize all the energy, but we can utilize a significant amount of energy that is available at that temperature gradient that we can utilize. Now, moving ahead, what are the potential applications? So, if you see the temperature gradient of minus 160, minus 162 degrees Celsius to like atmospheric temperature, these are the potential areas that can utilize that energy. Starting from the air separation, cryogenic CO2 capture, cryogenic emission, long-term storage of the biological materials, cryogenic treatments, dry ash production, and various other cooling applications like data center cooling, district cooling, etc. So this is the one work that we have already done. This work is for the utilizing that LNG cold energy for the 5 MTPA plant. 5 MTPA stands for the 5 million metric tons of standard plant to utilize the data center, to cool the data center of around 5,000 racks. So that can save around 35 megawatt of electricity. That can be potentially used for to cool the data center with the utilization of that cold energy. Now, this work focuses on the small scale LNG regasification systems. What happens when LNG comes to the regasification terminals? It's directly one way is to directly regasify it and transport natural gas for the long distance transportation for the end consumer use, like gas stations, household, or industries. Another way is we can utilize that LNG directly into the LNG stations in which the vehicles can directly use LNG as a fuel. And the other way is satellite stations, that are small scale stations around 100 kilometers, 200 kilometers, where the natural gas pipelines are not there. These are supplied as a LNG form, and then it is regasified at that satellite station. And this focuses on the utilization of that energy into the satellite stations. So in that regard, we have defined a few objectives, that is to develop a steady state model for RLNG cold energy utilization for the power as well as the cold application simultaneously. To conduct a comprehensive thermodynamic analysis of the proposed system, to assess the feasibility of the proposed system and quantify the avoided CO2 emissions as we are discussing the amount of electricity used for the conversion systems. Now, this is the proposed system. So this system having a LNG mass flow rate of around 800 kg per hour. So around cold energy available in this system is typically around 188 kilowatt. So we are using in the three applications. One is the ORC power generation. Second is the cold warehouse cooling, that is minus 15 degrees Celsius. And third is the ice slab making, that is happening at a 0 degrees Celsius. Moving ahead, so proposed system, we have analyzed the 4 different scenarios. First one is to directly utilize that cold energy for the, like in this in the ORCs, organic rankine cycles, in which the LNG cold energy is being utilized to condense the working fluid of that ORC, and room temperature water or atmospheric water is acting as a heat source, and this in between these two temperature sources, this organic rankine cycle is working. Second one is, and the rest of the LNG is getting heated by the atmospheric water or the sea water. In the case 2, that is the power generation plus ice making, the remaining amount of the cold energy in that case is utilized that case for the ice slab making. Rest of the parts is working as the same, and when we can't utilize that high temperature of energy, then we can just discarding at the seawater. Now the case 3, this 50 around from minus 92 degrees Celsius, we can see we are dividing it into two different applications. One is for the cold warehouse and the remaining amount of energy for the ice making. This is to decrease the temperature difference and to increase the system's efficiency that we are using. And finally, we are removing that ORC and directly utilizing a system that can be solely responsible for the cold warehouse cooling and the remaining amount of energy for the ice making. So these are the 4 cases I have compared, or 4 working scenarios of the system. So the whole system, all the 4 case scenarios are modeled using the SPAN plus simulation software, and all the property methods are calculated using the NIST databases. So these are the basic input parameters and the constraints that I have used. Coming to the methodology and the system assessment matrix, I have evaluated first what is the cold energy available in the LNG, what is the net work generated by the organic Rankine cycles, what is the energy efficiency of the whole system, what is the exergy efficiencies. Now, apart from the thermodynamic analysis, I have also done an economic analysis that all the economic cost of the purchase, economic costs are calculated using the cost equations, and we have calculated the internal rate of return to evaluate the investment feasibility. In excess of that, we have also done the annual cash flow analysis to evaluate the system's feasibility economically. So this is all the economic parameters that I've used. And in addition to the thermo as well as the economic, we have also done a carbon footprint analysis. As we are displacing the amount of electricity that is going to use, we are able to calculate what is the amount of CO2 that can be avoided using this system. Now coming to the results and discussion part, in the case 1, when only power is generated using ORC, we are having a system efficiency around 20.9%, and when we introduce the ice generation, we can increase that efficiency to energy efficiency to 34.3%, as well as we are also adding as one cold stream to generate a 50 megawatt of power. Apart from that, 39 kilowatt of power that we are generating with the overseas. So in the case 3, when we divide that 50 megawatt of cold energy into 2 different applications, one is for ice as well as the cold warehouse, we can increase that efficiency to 38.9%. Finally, the case 4, when we are not using ORCs, we are directly using LNG as a cold energy sources, we can increase the system's efficiency around 67%, and we can generate around 179 kilowatt of cold directly. Apart from this, in the economic analysis, we have done a total capital investment required for each cases. If we see that major part of that cost analysis is taken away by the purchasing economic cost, and to install that system, that's measured by the red and the yellow slabs. And other than that, if we see the internal rate of return, so case 1 is not showing any positive cash flow, that's why it's discarded. In the case 2 and case 4 are the most economical cases. In that case, we are getting the internal rate of return around 39.4% to 32% approximately. And the same thing is verified by the annual cash flows. As we can see in the case 2, that is ORC plus ice generation, and the case 4, that is warehouse plus ice, are only showing the positive cash flows and starting from the 3 to 3.5 years. And the rest of the 2 cases are still in the negative cash flows. In addition to the avoided CO2 emissions that are majorly based on the avoided electricity or the equivalent amount of electricity that we can save. So as we can see in the case 1, annually we can save around 286 megawatt hours of electricity, And in addition to that, maximum we can avoid around 821 megawatt of electricity annually, that can displace annual avoided CO2 emissions of 584 tons per year. Now, moving ahead to the conclusions, we have concluded that we have derived a detailed steady-state model for the cold energy utilization for the RNG plants using the as per the software. Now, in addition to that, a thermodynamic analysis demonstrated a maximum energy efficiency of 67.1% and the exergy efficiency of 37% with the optimal cold energy utilization. And the proposed system offers the potential to generate 39 kilowatt of power as simultaneously with the 50 mega kilowatt of power. Sorry, this is a kilowatt of cooling simultaneously. And the economic evaluation indicates the system's viability with a high internal rate of return of around 39%. So finally, integrating cold energy from this LNG systems can significantly yield the benefits, including annual electricity savings of 821 megawatt of hour with a CO2 emission savings of 584 of tons annually. Now, finally, this is the final slide that I wanted to show. The majorly, according to the REN21, we can see the percentage of global final energy used by the sectors cooling, transport, and the electricity. We can see the major part of we consider as the electricity, but that's the tip of an iceberg. The major part of that electricity is going for the energy is going for the heating and the cooling, so that we can significantly use that amount of cold energy to save that much amount of heating and cooling. Thank you.
So you mentioned, so for air most like for like they have to talk about the air. So they're kind of possibility to inhabit the air and into such a system.
Yeah. So for the large scale systems, that is around 5 MW plant, 5 million tons of plants. Liquid energy storage is a proven technology that Japan is already doing.
And the winds have battery storage, so how it may affect the efficiency and the cost? And the solve on that.
So currently, we see we are not utilizing any part of natural gas chemical energy. We are just using a thermal gradient. So anywhere, whatever the energy is being regasified either by the conventional system or our system, that is does not have any effect on that natural gas. We are just able to utilize that amount of extra energy that currently using that we are.
No question, I thank the speaker again. So our next speaker, I will